Hello, everyone. Good morning, good afternoon. Welcome to today's webinar. My name is Carmen Good. I'm your usual host from Technobis Crystallization Systems. And today I'm honored to introduce to you this new webinar hosted by Dr. Gerard Capellades. The webinar today, Quantifying Nucleation and Growth Rates from Population Balance Models in Crystalline. Just before we start, let me get to my right. I think you still see it, right, Gerard? Yes. Just before we start, I would like to give you a bit of information about this webinar. It's being recorded as we speak. It will last about 30 to 45 minutes. After the webinar, we will take a few questions. The recording will be made available to all of you after the webinar. Most probably my colleague Anastasia, she will share with all of you the place where we put it on our website, the recording, and also Gerard kindly agreed to share also the slides of the webinar with you. So they will be available on our website or on our YouTube channel to see them later. You are muted. If you have any questions, please make use of the chat function of this platform or write to us directly at info@crystallizationsystem.com. Also, afterwards, if you have any type of questions and you would like to have our assistance or Gerard's assistance, please send them to us or to him. I think he will also share his email address shortly, so you could be getting in contact with us. Just before we start, shortly about Technobis crystallization systems. For those of you that do not know our company, we are a Dutch company located in the north of the Netherlands, a world-leading technology provider for solid-state research, process development, and formulation. Active on the market since 2005 with more than 700 instruments installed worldwide. Some of you might already know our Crystal 16 or even the Crystalline instrument, looking at the names that joined us today, or even both of these systems. If you would like, after this webinar, to test one of our newest instruments, like the Crystal 16, newly introduced mid last year, and the Crystalline November last year, please write to us an email at info@crystallizationssystems.com or directly from, you can contact us from the website. Please remember the Crystal 16 is your instrument that helps you to determine temperature-dependent solubility, is your instrument for nucleation rate, induction time measurements, phase diagrams, and Crystalline with the camera technology that works exactly like a microscope. Also, if you have a Raman that you can connect it to this instrument, most of the Raman spectrometers out there are compatible with the Crystalline. It helps you in your developing or optimizing your crystallization process. It gives you quite a lot of information related to particle properties, particle size distribution, and so on. The crystal breeder is more the early discovery type of instrument, works at microliter scale. It's the gadget type of instrument that helps you grow nice single crystals. And now this is about Technobis. I would like to introduce our speaker today, Gerard Capellades. He is an assistant professor at Rowan University, Department of Chemical Engineering, and heading the Department of Crystallization Science and Pharmaceutical Engineering. He obtained his PhD quite a few years back at the University of Denmark, Technical University of Denmark, in collaboration with Glutamic. I think a very well-known company to a lot of us, many of us. And afterwards, he followed with a postdoc in the lab of Professor Meyerson and Richard Bratz. an impressive curriculum. I'm really honored to have you today, Gerard, and present for us today. I am going to stop here and give you the floor. I'm going to make you now a presenter. I think now you should be a presenter and being able to
Perfect.
share your screen. Thank you very much, Gerard, for joining us today and making this webinar available.
Thank you so much for the opportunity and for the great introduction. All right, so hi everyone. Yes, as Carmen mentioned, my name is Gerard Capellades. I'm gonna talk today about a little bit about how can we quantify nucleation and growth kinetics from population balance models using a crystalline. So I'm gonna start a little bit about myself. Yeah, as Carmen already introduced, I did most of my early education in Europe. I did my bachelor's degree in Barcelona. First encountered crystallization in 2012 when working as an intern with Lundbeck, and I did my internship, master's, and PhD with them. After that, I just moved to the US, working with Alan Myerson for many years. We actually started working together in 2015 during my PhD, and then I just came back as a postdoc. And yeah, in 2020, I decided it was the perfect year for actually moving across the country and starting a new lab. So I ended up just moving to Rowan, where I started the Crystallization Science and Pharmaceutical Engineering Group. In there, we're currently a team, a fairly large team of 2 graduate students, a third one, and maybe a fourth one coming in next September. And we have a lot of our research that's actually driven by undergraduate students on taking the bachelor's degree, usually third and fourth year, but we do have some people on the second year who are also joining us. A lot of the work we do is actually centered around the engineering clinics course that we have, which is essentially a research experience for undergraduates. They spend like 6 to 9 hours per week doing research with us, and I think they gain a lot of very valuable skills. We also introduce crystallization in the undergraduate degree, so in the third year. They have to take 5 weeks of crystallization lectures, and they have to know population balances and how to design, how to model a batch crystallizer, how to optimize an MSMPR, all that kind of stuff. So it pairs fairly well. It has a very good synergy with the research activities we're having. And the work I'm actually going to present today was actually led primarily by these undergraduate students. The first four authors in the publication were actually bachelor's degree students when they were doing that work. It's of course not the only project we have active. We do a lot of work in the field of impurity retention mechanisms in pharmaceutical crystallizations, as well as characterizing solid solutions. Part of this work is done with, is paired with investigations on solvent effects on nucleation and crystal growth. We thought that we had to automate the method so that we can have something that's a bit more robust, more consistent in between users and between sites, and be able to effectively screen for many systems. We also have some work on water desalination that was brought to us by visiting scientists, and we're continuing that collaboration. You're actually going to see more on this work on the crystalline, but applied to inorganic systems. But the focus of today is the early development. It's the early development in the organic pharmaceuticals. So a little bit of a overview on this. The methods are divided in 3 parts. First of all is the data collection. That's when you gain all the relevant kinetic information on the crystalline. That's when you collect the pictures of the crystallization process happening in real time. Then that data is going to be processed, basically cleaned up to figure out which is the range during the experiment in which you had significant crystallization activity for you to characterize, as well as a camera that is not yet saturated. So there's some cropping, there's some outlier removal. And after the data is processed, it's actually transferred to GPROMS formulated products in which we do the actual parameter estimation. We get the actual kinetic parameters out of this, right? Now, to give you an overview on the methods, we need to start a bit with the hardware, with experiments. All this work was done in version 1 because version 2. Yes.
Sorry for interrupting you. I think my picture is exactly on the slide. So I think if you can move it out of the sharing, because I think people
Yes.
would like to see the slides. And
Yes. Perfect. I thought
super,
that you were
perfect.
saying perfect.
Thank you.
All right. So this is what we have. So we're using version 1, right? And it's this. I guess if you're in this webinar, you already know more or less what the Crystalline does. But it's these 8 parallel reactors. We didn't have the Raman version, so we only have like process video. But essentially, you've got independent control of mixing and temperature, right? And you have some measurement techniques that you can use as inline turbidity to detect whether crystallization is happening or dissolution is happening, as well as some videos as combined with image analysis that allows you to tell what do we have in the how crystals are nucleating, growing, as well as the shape of the crystals. Do you have like oiling out, all that kind of stuff, right? All right. You may have been mostly familiar with how this instrument is used in either solidity measurements, like polythermal method. Crystal 16 is heavily used on that, right? As well as primary nucleation kinetics. There's a lot of induction time studies in literature, right? But if the experiments are designed correctly, there is enough information in there so that you can get information on the secondary nucleation kinetics. You can get information on the crystal growth kinetics, also the frequency of polymorphism if you run enough replicates on a certain solvent composition, right? And you don't actually have to detect the polymorph directly. You don't actually have to isolate it and measure it on the X-ray. There's a lot of ways that you can tell that there is actually some polymorphism going on. You can either have the Raman use, right? But you can also be able to see some changes in habit from image analysis, solubility changes. That's one of the main things that tell things. I'm going to show you some examples later, as well as some kinetic changes with the methods that we have, right? Crystalability, of course, if you have the pictures, you know how the crystals look like, as well as the occurrence of aggregation and breakage. Breakage is a bit more difficult, but in general, you can tell more or less how your system is behaving if you pay attention to those pictures, right? Now, the main question that we had in here was, can we collect kinetic parameters for secondary nucleation and growth from experiments in the crystalline, right? And we had seen some promising results on literature on measuring secondary nucleation under the assumption that the supersaturation is constant at the beginning and the initial rate of change in the number of crystals per picture, right? But we didn't see the population balance models that could be used to not just measure the crystal growth, but also the Capellade effects of supersaturation if that is not actually constant, right? That's something that we did not see, and we say, well, maybe that is something that we can actually bring in that would bring a lot of value. So the typical experiment that we would run is this dissolution and crystallization cycles, right? You start with a system that's usually has an excess of solids at room temperature, and then you heat it up until full dissolution. You cool down, and then after a certain induction time, there's going to be a crystallization event, and then you can cycle back to dissolving this material. The temperature transmissivity plot is going to look like something like this, right? You've got heating, holding, cooling, holding. And the transmissivity is going to tell you, well, the dissolution events as well as the crystallization events when they're happening. Now, these methods you may already be familiar with. It's the same recipes that are used for induction time studies. If you're not familiar with those, here's a very good paper that also explains some of the early work on that field, or at least on the crystalline. And this is actually intentional. It's one program, right? We want to implement the methods in something that's already being used so that there is not much of a barrier to actually utilizing this, right? You don't want to have to go out of the way to generate a very specific experiment so that you can get that very specific data point. If we can integrate it into something that's already been used, that is additional information we get at no cost to materials or time, right? And the idea is like you have this one program that has like, primary nucleation events, secondary nucleation, and crystal growth, and much less room for user-driven random error. One of the things we try to mitigate, not just because we have a lot of students cycling through the lab, but also because we want this to be transferable to other systems. And one of the problems we think with crystallization literature is that there is a lot of very different methods used for measuring kinetics. we're not very consistent in which expressions we use for supersaturation or what we use for particle size or the scales that we use, all that kind of stuff. So this was one way to standardize things. And we want to make sure that it's not user dependent to a very high extent, right? So yeah, unseated experiments, induction times, and then we collect data from there. So how does it work? This is again, the typical temperature transmissivity plot that you will get for a given experiment, right? You're already familiar with when people use this to measure induction times, that this one is based on transmissivity, but sometimes they use it based on the images. But what I'm interested here is what happens around the region where that crystallization event starts, right? And this is a video on real time of, if it's turning on, yes, of glycine crystallizing in water, right? And one thing that you can see is over time, you're going to see an increase in the number of crystals that you see in a picture, as well as an increase on the size of the crystals in the picture, right? And that's basically what inspires the thing. There is kinetic information to be collected here, and we need to find the most accurate way of retrieving that kinetic information of what's going on, right? So right now we have, at least in our instrument, we've got the capture rates that are limited to 1 image per second, and we're trying to have the fastest capture rates we can, so that especially for fast crystallizing systems, that is extremely important, right? And the software already provides the analysis that gives you basically the size distribution of the crystals in the picture, which is essentially, you can actually measure based on the number of counts how many crystals are detected, right? And you can tell information about the length, area, volume of crystals. I'm going to tell you a bit later about how to do that from the data that comes in, right? So on the image analysis algorithm, right, it is a typical picture of a running crystallization process, running suspension. And you pass it through the image analysis algorithm already implemented in the Crystalline, right? You will get a set of crystals organized in different channels, right? And from here, if you count, you can basically know the total number of crystals that are showing up in that picture. Now, this is assuming that it's dilute, and we're going to cover that in a little bit later. If you try to plot the number of crystals that you see in a picture throughout an unseeded crystallization event, and unseeded is actually important because if you add seeds, the camera is going to saturate fairly quickly. So if you start with an unseeded system, you're going to have a background with very few counts, right? When the solution is clear and maybe there's some dash showing up, and you're always going to have some sort of background. And then you're going to see an increase in the number of crystals detected in a picture, followed by a drop. This picture is taken from this event, and it's actually on this data point. This is close toward the point the camera actually gets saturated. So the early stages of crystallization is something that we're not very interested in for trying to get the kinetics, partly because when you have very, very low suspension densities, it is very difficult to model secondary nucleation. And I am not sure if the models that we're using for well-seeded systems are going to work so well at these conditions, right? High supersaturation, low suspension densities is not entirely what we seek for. And there's also a point on the other end in which there's so many crystals in a picture that you're actually going to start seeing overlap in the algorithm. And what used to be 5 crystals is now detected as 1, and that will actually bring the counts down on that instrument, right? So what we actually have is an optimal range from the point where crystallization is significantly active, that you can actually see a sufficient suspension density, to the point in which the camera starts getting saturated. That is the optimum range we want to target for parameter estimation, and we want to make sure that that one is as big as possible. So what do we need to target this? We've got some imaging trends that we can collect: number, length, area, volume of crystals in the picture. I'm going to show you how we do that. We have some solubility curves, solubility data from that system. We need some solid properties that are related basically to the model. And then that all feeds into a model that connects kinetics to a population balance and mass balance, and a supersaturation model that basically allows you to grab the experimental conditions that you used, provide the trends in particle size, and from those trends, you can tell secondary nucleation constants and crystal growth constants for that system, right? I'm going to start by diving deep on the structure of the model. Then I'm going to talk a bit about the imaging trends, and then I'm going to explain a couple of case studies. So, batch crystallization models. Most of you are already going to be familiar with this, right? As crystallization progresses, the system gets closer to, right? Yes.
Sorry for interrupting you. The slides are gone.
Oh, they are gone?
Yeah.
All right, let me share again.
Yeah.
Let's see. All right.
Yes.
Are we here?
Yeah,
Good.
and get rid of me from.
Oh, yeah. Yes, perfect.
Super.
All right.
Thank you.
No problem. Thank you for letting me know. So you're mostly going to be familiar with this, right? As crystallization progresses, you're actually going to have, an increasing solid concentration with a decreasing model liquid concentration. If you have negligible agglomeration and negligible breakage, you will also observe that the number of crystals in the system is increasing. The length of those crystals is increasing. The area and the volume are also increasing over time, right? Those are proportional to what we call the population moments, right? The 0th moment is actually telling you a number concentration of the crystals. First moment is a length concentration. And then second and third moments, they have some assumptions involved, but they are related to the area and the volume. Now, the idea with this is if you follow typical assumptions on a batch crystallization process, negligible agglomeration, negligible breakage, all crystals sharing a similar shape, as well as no size-dependent growth or growth dispersion. Those moments can actually be tracked as a function of the evolving nucleation and growth kinetics, right? And this is the expression, which for the 0th moment, it will become the change in number of crystals over time. It's going to be equal to the nucleation rate, right? And then first moment behaves like this, second, third, and fourth moment. The idea is if you know crystallization kinetics, you're able to track how the number, length, area, volume of the crystals is advancing over time. Now, the idea with this is if I know the third moment, if I know the total volume of solid that I've crystallized at any given point in time as a concentration, I can actually find out the suspension density of my crystallizer. You do that by converting from volume to mass in the density and also using a shape factor that allows you to correct for the fact that this third moment is assuming cubical crystals with a characteristic dimension that it's essentially the volume is equal to the length of the qubit power. If you have to adapt that to what is the actual characteristic dimension being measured in the system. We're going to talk about that for the crystalline in particular. But typically you would just try to calculate how much of that equivalent volume will correspond to the actual crystal volume if you're measuring that characteristic dimension. And KV can actually have a value lower than 1 if the characteristic dimension, for example, here was length instead of width. But anyways, if you have this KV, if you've got this density, you can actually calculate the suspension density, how much you've actually crystallized based on the volume of crystals that you have. If you know how much you've crystallized, you can use the mass balance to figure out how much is left in the liquid, right? So once I know how much is left in the liquid, I know my supersaturation, and then I know my kinetics, which allow me to feed back into the population balance. I'm going to show you this loop in a moment. But first, I want to make sure that we're also on the same page in terms of supersaturation, right? There's actually a lot of different expressions on supersaturation that you're going to see in literature, and it depends heavily on the field. If you go to a more applied studies, you're going to have a slightly different expression that some more fundamental studies are using. But fundamentally, it relates to the difference in chemical potentials between the solution at supersaturated state and equilibrium state, and the real fundamental definition of supersaturation for organic non-electrolytes. It's the activity at the supersaturated state divided by the activity at the saturated state, which you can tell from the concentrations and activity coefficients. Now, activity coefficients are really difficult to determine, especially at supersaturated conditions. So most of the time, the rate is assumed to be 1. We also don't like using mole fractions, which is assume that it's concentrations are grams per liter or grams per kilogram. It actually doesn't make that much of a difference. We've studied that already. But this expression is sometimes simplified as this. And you may see additional simplifications when supersaturations are low, in which you can drop the logarithm and get something like this. I've used that expression myself early on because that's what I saw in the literature. but we've already covered in prior publications the implications of using overly simplified expressions. We have the technology right now to calculate the logarithm. There is not much need to drop it. And the reason why it's important not to drop it, it's because, well, you can get significant differences in the dynamics of a system if you're using an expression that is not capturing the right trends in the driving force, right? So this is a system that we expect it's going from a high supersaturation to near equilibrium, right? If we're writing to that batch crystallization in the crystalline, if there's a significant change in supersaturation, we want to capture that correctly. So what we did was actually we used some methods that we that we developed back in 2019 with Meyerson. And essentially, we actually calculate the activity coefficients at supersaturated conditions and saturated conditions, and we calculate the supersaturation using an expression that accounts for the activities. So the way this works is you've got kinetics on the system. If they are known, you can track how the moments change over time. If you know how the moments are in a given point in time, you know how much you've crystallized. If you know the solvation in your system, you also know how much solvent is in your crystals, but that could just be zero if you don't have a solvent. And then, well, based on how much you've crystallized, you can actually calculate how much is left in the liquid, unit conversion to calculate the mole fraction. And then knowing how much is left on the liquid, knowing the sorbidity value, and some expressions for the activity coefficients based on the ideal sorbidity model. There's more description on the actual paper. You can actually calculate the supersaturation. And from that supersaturation, you know your kinetics. You keep solving that loop until the system reaches equilibrium. That's the whole basis of the batch crystallization model that is being implemented here. Now, the big question here is, well, we don't have the moments on the crystalline. We have projections of them, but we're not actually measuring the moments on the crystalline. And this is all based on the requirement that you know the initial moments and that you know, well, you have experimental data on how those moments change over time so that you can calibrate those kinetic parameters that we're interested in. So, how do we actually adapt? And that's the novelty of this work, right? How do we actually adapt the batch crystallization model to using crystalline data? So if you look at the sample that's crystallizing in the crystalline, right? The 80 ml vials that we use have external dimensions of 17 by 60 millimeters, right? And the camera will actually capture a small volume within that. We decided to call this theta, right? We just define this parameter. And if you zoom in, you will see that the camera will actually have a certain captured volume. You can very often see, if you're using the hook impeller, you can actually see the impeller on camera. So it does go pretty deep. And we also got some discussions with Technobis to make sure that we're getting realistic values on the volume that we're capturing. But we estimated it's anywhere, depending on the actual focus and everything, it's anywhere between 0.5 and 2 millimeters for a 4 micron per pixel camera. That's what we were targeting, right? Now, the other two dimensions, you can actually tell from the picture, right? You have a scale bar in there, so you can tell the height is 2.6 millimeters, the width is 1.9 millimeters, and the depth will depend slightly on the system. But we have a capture volume being very conservative between 2.5 and 20 microliters that's being measured in the crystalline. We're going to call this volume theta, and we can actually put it as a mass because we like using our models of mass instead. But it could be milligrams of suspension or microliters of suspension that are being captured in a single picture. Now, if we've got this value, what are we getting out of the crystalline? So this volume is actually much larger than what is found in most PATs, and that is why I don't really recommend using these in probe-based instruments, because they don't really go that deep, and you don't get that much data on a single measurement, as well as of course saturation. But you get the 2D projection that contains around 100 crystals with a certain size. So from this volume, you get a picture. There's going to be crystals at different depths. And keep in mind that what I'm considering here is the volume of crystals that are actually going to show up in camera. It's not the in-focus crystals. It's anything that will be detected by the algorithm. It's actually could be shown up in camera, but not detected by the algorithm. So it's something, it's not entirely the depth of in-focus crystals. It's not entirely everything that's being captured on the camera. It's somewhere in between, right? And it, of course, excludes the edges, because some crystals that are in the edges are not going to be captured completely. So the total area is also going to be slightly different, right? So that's why we define this as a separate parameter. So what we have in here is, you capture the picture, you analyze it, and then the crystalline is going to give you the, length of the equivalent area that you see on the 2D projection, right? Now, how do we go from there to things like the area or volume of the crystals on camera, right? Number is fairly easy to get, but to get area and volume, you have to make some assumptions. And we don't want to make many assumptions about the orientation if we have anything like needle crystals, because that is a whole probability aspect about where they are showing up on camera, like facing the camera or they are on the side, and how frequently one thing happens over the other. What we do is we limit these methods to only systems with a very low aspect ratio, so that we can assume that they have a cubical habit, right? So that the 2D projection on camera is not a strong function of the orientation of the cube. If we do that, then we can, and the description it's provided in the paper, supporting information, how we get the Ka and Kv, but we can calculate the area shape factors and the volume shape factors that translate from this cubical shape to a 2D projection gotten by the crystalline. Because keep in mind that even though we tend to say that for cubical crystals, Kv is equal to 1, that's only true if the characteristic dimension is the size of one of the sides of the cube. But in this case, the characteristic dimension is the equivalent circle diameter. It is not the size of the cube, so there needs to be some correction going on. That's why we use this Kv and Ka, right? So if we have that, we can now essentially use this theta value to translate from moments that we can get in the crystalline. Total number of crystals is the sum for all the channels of how many crystals do we see on each channel. Length is that multiplied by the length of the crystals. Then you have the area, length square, volume, length cube, but then you have to correct by these shape factors. And using that, you can actually do a scale adjustment, assuming, of course, that the particle size distribution is representative, that the captured volume is large enough and deep enough from the wall of the vial, in which is going to have slightly different fluid dynamics, right? So we need to assume that it's a large enough capture volume that whatever we're capturing there is representative of the full system. Of course, mixing is also important in that sense. So using that, we can actually convert from the moments that we see on camera, the number, length, area, volume of crystals on camera, to the moments that we expect in the final crystallization volume, right? Now, noting here that total number of crystals on camera, it's only depending on the number. This depends on number and size, but those two also depend on number and size. So they are not independent metrics. We really only have two measurements. We really only have the number and a measure of size that could be either length, area, or volume. So that is important on parameter estimation. We didn't use all four. We only use number and usually area, but I'm starting to get more inclined towards using length because of noise, essentially. So if we have these methods, now we can go to a traditional batch crystallization process, the model, and then we can replace the moments by these projected moments that are now a function of things that we can actually see on camera. If we do that substitution, now all we need is the data of the number, length, area, and volume of crystals over time, which is, of course, calculated under the assumption of cubical crystals to get that third dimension, because projections are only 2D, right? And then from getting those, we can actually calibrate our kinetics. Now, how do we get those? Well, we've placed the model. This is how it works. To process this data, what we have is two steps. First of all, we find this range to crop, in which we want the crystallization to be active enough so that the initial conditions are already on a well-seeded system, right? Even though we're actually not seeding, it's just a primary nucleation event. And then we also want to stop before the number of crystals per picture peaks, somewhere around 80% of the maximum value. That's when we just crop things. We also have some outliers, right? Especially if you're using the hook impeller, sometimes it will show up on camera, and that means that less crystals are going to be shown up because part of the camera is being covered by the hook. So we have an outlier detection that we just basically remove everything that's far off from a moving average. We've automated all of this in an Excel file. If you want access to it, please let me know. We'll be happy to help you. But it's essentially, it crops the values where you copy and paste the crystalline data. and then it does the cropping, it does the initial values for GPROMs, it calculates those, and it does the outlier removal based on user-specified boundaries. And it asks you to validate that, it did it correctly, because some systems that crystallize very fast are going to behave a bit differently, and you need to make sure that the cropping makes sense. So it gives you the full distribution as well as the crop distribution. And if you're satisfied with it, you copy and paste the GPROMs, and then you have your parameters set. So this is how the process data looks like for an acetaminophen experiment, right? And these are the trends in number, length, area, and volume of crystals per picture, which you can see start getting noisier over time because of the error propagation and using that length multiple times. Now, because they are not independent, length, area, and volume, we only use one of them. Initially, we were focused more on area because we thought, well, technically we're seeing area, but probably for error propagation, length may actually be a better option, especially if you have a camera with high magnification. So this is how we do the kinetic screening in that sense. So now we basically know how the model looks like. We know how to process the data. We know how to get the actual data in there. So some examples. The first case study that we presented in the paper is crystallization of acetaminophen from ethanol water. This is a solidity curve. This is how it looks like for in the solvent composition as a function of temperature, right? And we decided to take 4 different supersaturations for the analysis. So we were working at 10 Celsius, and we decided to do 40, 50, 60, and 70 milligrams per gram of solvent. Somewhere that has a high enough supersaturation so that you can get, a reasonable induction time, like no longer than, a couple of hours, but also low enough that you don't have immediate nucleation before you manage to cool down all the way to the final temperature, right? And then you get those 4 values. With 4 camera modules, you can actually do entire screening in one day. It takes about 3 hours per cycle. If you do 4 replicate cycles, it's fairly easy. You can just do it in 12 hours. And then what you essentially have is these are the trends in crystals per picture, right? What I'm having in here is 4 replicate events, and you can see them. They are organized by color when it comes to the concentration, and by shape when it comes to the replicate event. So those are overlapped experiments. You can see that in some cases, like these triangles in here, this event was slightly faster than the others, right? But generally, even though the data shows noise, the important thing is that we can see kinetic trends beyond that noise, that higher supersaturations mean that we're getting faster kinetics despite the noise in the data. And that's what we're looking for, right? The experiments are repeatable. That's the idea, right? So if we have those trends, we can process them, we can run them on parameter estimation, because it was the first time we were doing this, and we want things to be comparable between systems. We wanted to limit the amount of parameters we get per kinetic rate. So we only asked the system to estimate KB, KG, and theta. We assume the values for B, J, and G. It's also easier to be able to compare different systems because there may be some small correlation between those parameters, and then it's much better to just keep it to one value that expresses how fast nucleation is, one value that expresses how fast growth is, if everything's kind of the same. Now, of course, this means that if the assumption is not correct, the fit is not going to be quite as good, but we're willing to deal with that. So we got this KB value, this KG value, and then a theta value that we allowed it to adjust. And that's partly because this is something that's going to be slightly system dependent. Larger crystals are more likely to hit the edges of the picture. Therefore, the effective area for capturing is going to be smaller. Slightly different focus may change things. Also, because this is based on mass, difference in density will also have a small impact. I don't expect to have a 50% chance, but 10 to 20% between different experiments, that's something that between different systems, that's something that I would still be okay with. And what we did with the theta that we estimated is we saw whether that would make sense based on the based on the depth that would imply, and it's somewhere around 1 millimeter. That's basically what we were expecting. So these are the kinetics that we got for the system. Now the question here is this reproducible? So to figure that out, this was done in a 4 micron per pixel camera. So it's the lowest possible magnification. We're going to talk about that in a moment. But we decided to, try to repeat the same experiments at Pfizer. So different users, different crystalline, different raw material. They basically just, got their own acetaminophen, repeated the experiments themselves with their own camera. Now, the difference here is that the camera was 2.8 microns per pixel instead of 4 microns per pixel. That means it's a different theta, right? So this is the capture volume that we determined at Rowan, right? And the capture volume that they were expecting was going to be, of course, a lower area because it has a higher magnification and probably also a lower depth, right? But yeah, the 2D area that was being captured was 2.4 millimeters square instead of 4.9 millimeters square. That essentially means that we expect theta to drop at least 50%, if not more, because the depth may also go down with that, right? So what we did was we used our kinetics that we determined for this system, and we tried to predict the results, letting the software only correct for theta, right? And see what theta it's correcting for. And what we got was 59% drop in theta. It just got to 2.26 milligrams per picture instead of the 5.6 that we had. And we got a reasonable fit if we adjust the theta to actually a realistic value based on what we would expect by decreasing the area by around 50%, right? We also tried, just to make sure that it was not that you could just change the theta and you can make anything fit. We tried with kinetics that we got for glutamic acid and other systems to see if that could even work. And no, there was no way close to a fit. So yeah, you need the prior kinetic parameters that would make sense for that system in order to be able to estimate that. But yeah, this is the reproducibility that we showed in between sites when you actually have different crystallines with different magnifications. Now, the problem here, and one of the things that we had to change in here, is that we were using crystal length instead of area. And the reason for that is noise. The data on area was far too noisy. This is our cameras. This is the 4 micron per pixel camera that we have on the left, and this is the 1.9 micron per pixel camera that we have. Same experiments, same conditions, right? This is the data that we get on the 4 microns per pixel. This is the data we get on 1.9. You really want to use these methods in magnifications like 2.8 microns per pixel or technically lower, right? You want to have very low magnifications. Why? Because you want to maximize the signal that you're getting in a single picture. The overlap will happen much sooner if you have higher magnification, because at the same crystal size, they are more likely to just cover the camera. And also, it's going to be more difficult to figure out the trends. So the idea is you want very, very high magnification, very low magnification, so that you can actually capture as many crystals as you can, so you can capture clean trends. If you try that with very high magnification, if you try that with a system that you see it, you're already starting all the way up, and you're not going to see anything that any trend that will have a value for these methods, right? So that's our recommendation. If you have those cameras, use those cameras. 2.8 still works, but just use length instead of area. Now, second case study, and yeah, doing more as well. Second case study was glutamic acid crystallization from water. And that's a system that showed significant polymorphism, and that's one that we wanted to see how does this behave with polymorphism. So we did the same. We selected 4 conditions. In this case, we had to select much higher supersaturations because this system crystallizes way slower than acetaminophen. So if you wanted reasonable induction times, we had to go a little bit higher on that, right? And these are the events we got, which, as you can see, there's already much more data because it was a much longer crystallization event. This is a slower system crystallizing. We saw similar levels of precision observed for acetaminophen, but we needed those higher supersaturations. We also saw polymorphism. Most of the time, we crystallized the alpha form, especially on concentrations 35 and lower. But sometimes there was a transition to beta form during the actual experiment. This is what I mean, that you can get out of indirect metrics. You can see where your system is behaving for polymorphism or not. A very obvious one is, of course, the change in shape. But also you can see a change in the dissolution temperature, a change in solubility, because if you crystallize it from polymorph, it's going to have a different solubility, right? And sometimes you can also see it as a change in kinetics. So these are 2 experiments on the same starting concentration, 2 different polymers. You can see that most of the experiments are actually reproducible within themselves, but sometimes you'll actually get one event that's way faster than the others, and that is also combined with something like a different shape, combined with something like a different solubility value. That is a strong indication that you have some polymorphism going on in the system, right? So we focused only on the alpha values. It was impossible for us to find, or at least not worth the time, to find the solubility values for the alpha form, because it was always transitioning to beta during the slow heating that you need for the polythermal screening. And offline screening defeats the purpose of the simple experiments. We ended up just taking the alpha solubility from literature, and we did the parameter estimation for that. So again, we got the parameter estimates. We assumed the values for B, J, and we let theta float. And after letting it float, it actually converged into the same value that we were getting for acetaminophen on that camera. Yeah, it overlaps exactly if you actually convert from mass to volume. And we got these different parameters. Now, there's going to be some correlation, especially if you don't have a strong variation with the with supersaturation on your trends. There's going to be some correlation, especially between KV and the theta value. To break that correlation, you really need to make sure that the theta value you get makes sense. Otherwise, it's just going to float everywhere. And you can see that from the model, how it's designed. So it is very important that you really, now that we know more or less what it should look like, that we constrain it to very, very small range within that value, so that you can actually compare different systems. Otherwise, with a correlation between that and any kinetic parameter, there is going to be challenges with being able to compare different systems, right? So this is a comparison of the raw data between two different compounds, right? These are the kinetics for acetaminophen that you saw that was already at lower supersaturation, so it was closer to equilibrium, right? 300 seconds to saturate the camera, even at the lowest concentration. This one, the highest concentration was 300 seconds. It took much longer. That's why you see a much higher density when it comes to the number of data points that we obtained. Glutamic acid was very visually slower than acetaminophen was, right? Do our kinetics say the same? Yes. What we saw was on our kinetic parameters, we saw a drop in the nucleation constant by a bit more than an order of magnitude and a factor of something like 8 on the growth. So that is something that we managed to capture on the kinetics, and that is part of what the value is of these methods, right? Now, there's the big question that I know I'm going to get, and I prefer to address it now in the presentation than in the questions directly, right? Are those scalable? And no, the answer is no. They are not scalable. That's not the point, right? We already know that secondary nucleation is sensitive to mixing conditions. If you scale it to different volume, you're actually going to have different mixing conditions, different frequency of collisions, different fluid shear around the crystals. You're going to have a different secondary nucleation rate. But to actually show how different they are, we actually ran some MSMPR crystallizers at the 150 milliliter scale. So that's like 30 times larger than what we were doing in the crystalline, and in continuous mode. We let them reach equilibrium, and what we did, steady state. And what we did to have a fair comparison was we took the samples from the MSMPR, we dilute them to a suspension density that would not overlap the crystals on the crystalline, and then we analyzed them for 10 minutes to figure out what the particle size distributions were on the crystalline. So what you can see is that the prediction was actually over-predicting particle size and under-predicting the concentration, right? So probably we had a faster nucleation rate in the MSMPR than what we had in the crystalline, but that's not the point. The point on this is not the scalability. It's the use, their precision, their consistency in between groups. This has a value for fundamental academic studies, right? So if you're not so concerned about scalability, a lot of our understanding of nucleation has come from induction time studies at these scales or lower, right? So this is a way to understand factors that affect nucleation and growth that is very valuable in academia, right? As well as developing secondary nucleation theories, which are fairly abandoned, right? In industry, it's also useful for early screening, early studies. So it helps you to narrow down the design space. early on. Very limited amounts of material, very limited amounts of time. You run this, you figure out more or less how your system behaves before you run the final experiments, the final parameter estimation, if you're going that route. You can answer questions like, is this system a slow nucleator? Do I even need to consider having wet milling or sonication ahead of an MSMPR, for example, right? Or does this new molecule crystallize more like acetaminophen or more like glutamic acid? What kind of residence time can I expect to find? What kind of challenges can I expect to see if I'm going for a certain crystallizer configuration? When getting your kinetics, can I make assumptions in the way of like, temperature is not going to have a significant effect on kinetics, or solvent is not going to have a significant effect on kinetics? All the kind of stuff you can investigate at the lower scale. An anti-solvent is an anti-solvent at smaller scales as well as larger scales, and that happens with solubility. It should also happen to a certain extent, unless there's some mixing limitations with kinetics, right? And that's the idea. If a solvent is slowing down nucleation, it's most likely, or impurity is slowing down nucleation, it's most likely going to slow down nucleation at a larger scale. These are the kind of investigations you can do with a very small amount of material, right? Polymorphism, right? How much more likely it is to form a certain polymorph in this anti-solvent fraction? How much faster does it crystallize? How is it going to behave? All the kind of information you can get with quantitative values, right? The value here is in precision. It's like when we use things like FERM. We know that the chord line distribution we're getting is not a real particle size distribution because, among other things, depends on the definition of particle size. But we use the trends, we use the kinetics, right, to show, well, there's growth going on in here. There is nucleation going on in here. This system is faster than this other system. And that's essentially what we're targeting here, right? The idea is that we see a lot of work that end up having like dozens of experiments, maybe on MSMPRs. I've done that myself in my PhD. At scales that are very time and material intensive to calibrate all these parameters, right? Get activation energies for nucleation and growth, all that kind of stuff, only to realize that maybe temperature has a very small effect on kinetics for that particular system, or that solvent composition matters more than, or that the impurity is actually going to inhibit things. So this is a way to narrow down the design space early on, right? So you incorporate this rapid screening to save time and material early on. And then you use that information to be able to design the final experiments, to know, well, I'm not going to investigate the effects of solvent composition within this range because I saw that there's not a strong effect. I'm not going to investigate the effect of temperature because I already saw that, it's not the main factor. It's this kind of information that you can get from this data, right? It's not so much about replacing parameter estimations on the 100th to a liter scale using PATs and all that kind of stuff. It's more about the early screening. That's its place, right? At least my view on it, right? So with that, I want to thank a lot of the people who did the work. There's a lot more people that I would have to thank who are actually expanding this work. We do have other students and visiting scientists who've been working on expanding this for inorganic systems, and there's a lot more papers coming on this field. But the focus of this presentation was on the published paper, and this was driven primarily by our bachelor's degree students, our engineering students, and we also had like 2 master students who were helping advise those students. Yeah, Griffin, who's now graduated and moved to VCU for a PhD in crystallization. So he's going to be with us within the field. And Ibrahim, who's doing his master's thesis with us now. I also like to acknowledge Pfizer R&D for funding, as well as the amazing advice I got, especially from Kevin and Alpana. They've been great at shaping this project so that we would actually have something that made sense and that was going to be industrially useful, right? So with that, thank you very much, and I'm open for questions.
Thank you very much, Gerard. I must be sincere with you. You have already answered a few of them.
Nice.
So the one also with the scale up, it was already there, and then you started with your slide. So
I knew it.
Yes, indeed. So you already answered a few of them. I have already written in the chat. Unfortunately, we do not have that much time. We are almost. It's almost 5 o'clock now. I will share everything, and I see clapping hands for you, Gerard. I will share them with you after this webinar, and maybe we can answer to each one of these questions. And it was really nice to see the work. I must be sincere with you. So you have used the version 1 of the Crystalline, so the older version. Nowadays, the version 2, the software and the image analysis, it's a next level, let's say. It's already taking, I don't know if you heard about it. It already takes into account the volume, so it calculates. You don't have to do all these calculations, that some of the calculations that you have additionally done. Also, the technology itself is a bit different in terms of lighting, the front light and so you see less, say, noise, or how to call it. You also call it noise, and so also the advanced analysis package, where when you see 2 particles, it will detect 2 particles, not 1 big particle. So quite a few things are actually different. Maybe we'll have the chance to actually redo something together, a project on the newest one. Definitely at Pfizer, I see the group, and we are in contact with them, and they have it, the newest one. So maybe something for the future. And always nice to see that actually from maybe people, they do not realize always, from the images and also from the transmissivity, you get so much information out of it. It's not just it got into the solution or crashed out. You can also get information about, okay, here might be that another form is formed, and so that definitely. Okay, so I will stop also. I talk too much as well. We are a bit later. I will share with you the questions. And we will try in the coming week to address them. Thank you very much once again. Really nice webinar you have shared with us. Really nice data. I do recall we were in contact via my colleague Fernando for quite some time now, and I'm happy that now the publication is out there, is published, and we were able to make it available. Thank you all for joining this webinar. We will be back with an email showing to you where you can find the recording to rewatch this. Already somebody asked about the slides. If they are available, will be available on our website to download them and have, again, a look at them. And we will address also the questions. Still, if you still have questions, write to us or directly to Gerard. Thank you all, and thank you, Gerard. All have a good summer. We will be back in September with our next webinars.
Thank you so much. Yeah. Right. Bye.